So we were talking about Big Bang nucleosynthesis, and I tried to show you the reaction networks and also how beautiful an observational probe of the Big Bang model it is. And so if we go to what I showed you before, saying that stars are cosmic pots, you can see here in this view graph, before we go to nucleosynthesis again and stellar one, when we compare Big Bang nucleosynthesis abundances to solar system abundances, we have variations. In particular, you see that part of the hydrogen has been destroyed. It's been converted into helium. And part of helium, which is here, has also been modified or transferred or served to synthesize the metals, the heavier elements. And this value is an old value for the solar system, which was 1.7%. The new value of the solar system is more about 1.4%. You may ask why is it important, but actually these tiny bits of metals, they are crucial to stellar evolution because these heavy elements are the ones with which light interacts the most. So they contribute a lot to the opacity of the plasma, stellar plasma. And so they drive the evolution. They are also an important way to understand the evolution of stars. And so going from 1.7 to 1.4 doesn't seem much, but can revolutionize or just shake a bit the stellar community, as it happened 15 years ago. So let's move now that we have the X and the Y, let's move to the Z. And let's move to the stars, because that's what happened between Big Bang nucleosynthesis and today, or when the solar system was formed. This is stars. So I didn't put a plot of the cosmic evolution. You might have seen it several times. This plot can be shown in different ways, but you have a kind of a cone where you have the Big Bang, and then you have the dark ages, reionization of the universe becoming transparent, and then structures appearing. And we think that stars appear before, or it's a bit like the hen and the egg. We never know who happened first, but we think that stars happen first, and then they are structured into galaxies, and galaxies are structured into clusters of galaxies, and we can study the evolution of all these fractal scales in the universe. But stars happen first, and as you may understand already, we will come back to it later, the first stars that happen are devoid of heavy elements, and so they will have a very peculiar evolution. Up to now, there are theoretical models of it, but of course no observations. Even though with the James Webb, you might have seen, it's actually not a James Webb achievement, it was a Hubble Space Telescope achievement. There was an observation of an individual star, which is quite rare, I think it's the only one, in a lensing event. So for those of you who are not familiar with astronomy, gravitation, as I told you, in the universe, the matter, and it's shown normally just for divulgation. You can see, if you see the universe as a sheet, and you put massive things inside, let it be clusters of galaxies, which is the case here, so very massive things. You put them on a sheet, and you will see the sheet just adapting to the wave, so it will change the topology, and that's what happens with mass in the universe. So the mass changes the topology, and very massive things, and it's one of the predictions of the general relativity and Einstein theories, is that they can change the topology locally so that the mass acts as an amplifier, as a magnifier, visual magnifier. It's called what we call lens, gravitational lenses. So it's a lens, but instead of being an optical lens, it's a gravitational lens, meaning that as you curve the space-time around the mass, you will have appear, you will see things that are beyond this what you observe actually, that are far away, but you can see their image due to the lens that is done by the curving of the space-time. So you have kind of a gravitational lens. So this is a way to observe very distant structures of the universe. And because they are distant, they are also old, because light travels at a finite velocity. And so when we observe far away, we observe also earlier times of the universe. And so HST observed a star. I don't remember what's the name, but it's the name of whatever, an elf of the Lord of the Rings kind of thing. That's Elberet or Alderael, or I don't remember. So, but it's an elfic thing, just like, you know, elves never die, and they are very old, so that's why. And so there's one that has been magnified, was magnified with HST, was found a multiple image of this same star, single star. And thanks to JWST and spectroscopy, and they were able, last year I think, to determine the type of star it is, its mass. It's a B-type star, so it's a quite massive star. And so we have thus a tiny quick look on very, very old stars, and maybe if we find others like this, we can constrain the primordial evolution of stars just after the Big Bang, even though it's still a bit beyond our grasp, but maybe we're getting there. So these stars, which are called the population 3 stars, they will be formed only out of hydrogen and helium and their isotopes. And so they will have a peculiar evolution. We think they are very massive, and this JWST observation confirms that they are massive stars. And I will come to it a bit later when I describe what kind of nucleosynthesis happens in stars and what happened in these stars. So stars. This is more my specialty. I have to do everything in a nutshell, so I hope I don't lose the ones that even if I lost you a bit in the first part, don't worry. We are going back to light bulbs and easier things. Stars, even though the stars are very complex objects. So stars, they can be classified according to many criteria. There are lots of criteria, and depending on if you are studying stellar evolution or exoplanets, or if you are doing galactic evolution or whatever, you have several ways to classify stars. The main ways, and the historical ones, are the classification using photometry and spectroscopy, which help us, because stars, we don't have them in labs, and it's not like in Marvel movies. We are not able to build stars in laboratories. And so everything that we know, which is always kind of another magical thing, we saw the magics of tunneling and quantum physics. There's a magic in our understanding of the universe, because we have to always think that everything that I will say and that I say about the universe, we know through only analyzing the light of stars or dust or things. And it's quite amazing that we have such an amount of information, powerful information, just analyzing the light. And so photometry, as you all know, so here you have these light bulbs with the colors going the opposite way from the bath tub. So the red is cool and the blue is hot, and this is due to the Wien law. Here you have. So the density energy according to wavelength, and you have a one-to-one relation between the maximum wavelength and the temperature. So doing photometry, and so finding the maximum of energy in one spectrum. Here, for instance, this is the maximum of energy in this kind of stars. Here is the maximum of energy in this kind of stars. You can see what's the temperature. So, okay, it's just the surface temperature, but it's already okay. And then if you look at the sun, for which we have hints of the central temperature, you can calibrate your stellar models, and then from this yield a central temperature, which is what we want for nuclear thermonuclear reactions, because as you may expect, even though we have stars that have surface temperatures up to a few tens of thousands, a few 10 times thousands Kelvin, so the very hot ones, it's still much lower than what is needed for nuclear reactions. So nuclear reactions don't happen at the surface of stars, it happens in the center. But we can, with the surface temperature, surface gravity can also be measured using spectroscopy. And what we know of the sun, we can infer the temperature in the center of the stars according to their color, which is also related to their mass. So this is the Harvard classification, which, by the way, was done by, you might know them or have heard about them, but in stellar physics and stellar nuclear physics, lots of results are due to women in the earlier 20th century. And so this classification is due to Anne Cannon, among others, which are the Harvard computers. So these are human computers at that time, and you can find lots of things about them, very interesting. And so these women, they classified the spectra using photographic plates, and they classified them according to the lines that appeared and the color. And so this catalog shows you that a blue star will be an O-type star. It's very hot, 30,000 Kelvin at the surface. It's blue, and there are lots of ionized helium. And you see that there's lots of flux here in the blue, but not that much here in the red, green, and red colors. So it means that the peak here of your energy distribution is in the blue. Okay? And then, so you have this, there's a sentence, I never remember it, and even though I would remember it in French, so it's useless for most of you. But there's a sentence to remember the series, so because it's not alphabetical, it would be too easy. So it's O, B, A, F, G. This is us. Well, not us, the sun. It's a G-type star. K and M. And so M stars here for exobiology, they are very interesting. We've heard yesterday several of you working on the TRAPPIST system, or knowing about it, or working on the habitability around these M stars. And these M stars, they are the majority of the stars in our galaxy. It's not the sun. The regular star, it's an M star in our galaxy. It's not a G star. But the sun is a G53, something like this. So there are lots of numbers. Just to tell you that it's yellowish, actually, the peak of energy is more greenish. And you have energy, most of the energy here, less blue light and more red light. And for the M stars, they are very cold, less than 3,700 Kelvin. And they have a peak of their luminosity more in the red. And that's why we are looking at them, because they are small, they are cold, and so the habitable zone, which is the region in space where liquid, in the first very simple way, there are much experts in this room about this, is for having liquid water at the surface. So these are the physical conditions, and for the M12, it's much closer to the star. And so it's easier to observe, just this. That's why we look at them. And we have lots of things. So this is a first classification of stars. Stars in a nutshell, part 2, their structure. So a star is a ball of plasma. It's not a great ball of fire. It's just plasma, and it's not burning, even though you will hear me talk about burning. It's just there's fusion somewhere. So the internal structure is determined by a set of conservation of laws of not odd physics, sorry. And And so the laws are conservation of momentum, conservation of energy, and several other ones, conservation of matter, and equation of continuity. And when you solve these several equations, it gives you the structure of a star. And these stars, the fact that we observe stars means that they are here, they are in equilibrium, they are not collapsing every second. And so the fact that they are here, it's because in a star, a normal living star, but also in dead stars, as you will see, there's an equilibrium between gravitational forces, which are applying everywhere in the universe at all ranges, and an internal energy source that varies with time. And so these stars are essentially in what we call hydrostatic equilibrium, which means that when you solve the momentum equation, so velocity of the plasma equation, what you have is that temperature, density, and pressure depend on depth, just like when you go down in the sea or in a pool, you can really measure this stratification. So here, if you take a portion of a star, you will have a shell, for instance. You have each shell has its own weight, and it's surrounded by matter above and below. And above, you have the downward pressure exerted by the upper shells, and downward, below, you have the upward pressure exerted by the lower shells. If the pressure exerted by the lower shells is not enough, as you will imagine, gravitation will win and the star will collapse. Okay, and this happens in some parts of the star, all over their evolution, and it also happens in some phases of the stars, and it's the end of their evolution. So the pressure that we have in the center is exerted mainly by radiation and also by intraatomic forces when it's a dead star. So when it's a dead star, you don't have nuclear reactions in the center. Now you know what I call a living star. And so, but still the stars are still here. What are dead stars? The dead stars are white dwarfs, neutron stars, and stellar black holes. Okay, so these are the three stellar remnants. Also, you can find these wording. And in these stars, it's not nuclear energy that provides the amount of energy that lifts up the shells against gravitational collapse, but it's the intraatomic forces, either what we call electron degeneracy, electrons when the matter is very compact due to quantum mechanics knowledge. They are, and what we call the Pauli exclusion principle, they hold together and they are packed, and they packed with opposite spins in cells in the momentum space. And so this exerts a pressure, the electron exerts a pressure that prevents the star from collapsing. But if the mass of the star is too high, then if the electrons won't hold against gravitation, and nuclei will be broken, and we will go back to the primordial soup of neutrons and protons, and it's neutrons that will hold the star. And for the most massive stars, even neutrons won't be enough to hold, and you will build what we call a stellar black hole. Okay? So these are the dead stars. But in each case, there's something remaining, an object that you can measure its density, measure its radius, measure lots of things. And it's because you have an equilibrium between pressure and gravity. So this equilibrium is also related to the energy generation, as I already said. So the energy conservation, when you solve for this in a star, it yields that the stars are in local thermal equilibrium. They are not in total thermal equilibrium, otherwise they wouldn't radiate. We wouldn't see stars. There would be black bodies, and by definition, as we are always very explicit in astrophysics or in physics, what is black cannot be seen. Okay? You don't emit any radiation. But the stars emit radiation. It means that they are not in total thermal equilibrium, but they are in local thermal equilibrium, and they radiate energy at their surface, and solving some equations shows you that the energy radiation at the surface is compensated by the production of energy in the interior. The thing, for a long time, the question was, where does this energy come from? Because of the first part of the lecture, you now know that this energy may come from nuclear fusion. And, but we had, as you know, we have been studying stars, astronomers have been studying stars since a very long time, and have been studying stars in a scientific way since at least the 17th century. But we had to wait until the 1920s to actually answer this question, because we needed first specific relativity and the equivalence energy and mass, and second, quantum mechanics for the tunnel effect. And the one who understood this first was Sir Arthur Eddington, who published in the observatory this paper, which is called The Internal Constitution of Stars. And this paper followed an experiment of Aston, who had a mass spectroscopy, did a spectroscopy of mass, and had measured the mass of a helium nucleus, and seen that the total mass of the helium nucleus was lower than the sum of the mass of the protons and neutrons that make the helium nucleus. And this is the mass defect that we talked about during the first part of the lecture. Okay? So there's energy because it's a massive thing, and it's not just the sum of the energy of the masses of the constituents. There's something different. And so he wrote this. So there's a long paragraph saying that they've come to a dead end, and we have to find where the energy of stars comes out. And he refers to this experiment, and he says that helium is made out of hydrogen. And so if 5% of a star's mass consists initially of hydrogen atoms, which are gradually being combined to form more complex elements, the total heat liberated will more than suffice for our demands, and we need to look no further for the source of a star's energy. So we have to wait to 1920, and this equation, the equation of Einstein, was published in 1905. So you see that there's some years before it percolates and goes to stellar astrophysics. So now we know that the energy of stars is provided by nuclear fusion. And so in the end, a structure of a star is determined by two equilibria, gravitational equilibrium, the hydrostatic equilibrium, and a thermal equilibrium. Okay? So you have pressure, internal pressure from the photons that are emitted by nuclear reactions that sustain the star against gravity, while there are nuclear reactions, and when there are not nuclear reactions anymore, it's other forces that maintain the star against gravitational collapse. And then you have a radiation at the surface, which is compensated by this energy that is made in the center of the star. And this cartoon shows you a cartoon of the sun, the interior of the sun. So for those of you who are not astronomers, and there are a lot of you, so we model stars as spheres, which is the first approximation, which is more or less okay for stars that do not rotate rapidly. Otherwise, they will look more like rugby balls, which are, we have observed them with interferometry. And inside the sun, we have three parts here, which are fully artificial. But the red part is the region where temperature is high enough for nuclear reactions to occur. Okay? And then the difference between the two colors here is that here the energy is transported mainly by the photons escaping. And here in the orange part, the material is opaque, is too opaque. And so the energy is transported by convection. So convection is what develops when you put water to boil. Not when it boils, because when it boils you have change of state and it doesn't work, but just before it boils. You have these convective patterns, which are large-scale patterns that efficiently remove temperature gradients, so homogeneized temperature gradients. So now that you've seen this structure and that I told that the energy is made of thermonuclear reactions in the core. The thing is that you may say, okay, the star is built out of more than 70% of hydrogen, but the nuclear reactions only occur in a tiny bit of the star, the very center. And at some point, if you wait long enough, nuclear reactions will occur at such a rate that you will exhaust all the hydrogen. At some point, all the hydrogen is converted into helium, okay? And when this happens, you don't have the fuel anymore to sustain your star against gravity. So what happens if you don't have anything that goes against gravity? Gravity wins, and so the core contracts. If you assimilate the stellar plasma to an ideal gas, which is a good approximation, when you contract, you will have an increase of temperature. And so again, if the temperature increases enough, you will again be able to provide enough energy for heavier nuclei to overcome the Coulomb barrier and to go into nuclear fusion again, okay? So nuclear fusion is really the fuel of stellar evolution, meaning that it occurs, the star, just like the sun, is maintaining its structure. At some point you get out of fuel, the core collapses, the temperature increases, and then the seed of hydrogen burning, which is helium, will again be able to fuse, and we will go on. Up to now, what we saw with Big Bang nucleosynthesis is that from a nuclear point of view, it's difficult to go beyond helium, okay? So we do not really know how to make carbon because we don't have these stable isotopes with the right masses that we want. And we will come to it in a moment. So this is a scheme with temperature here, and here energy or stellar luminosity. And what you see is that in a star, all the evolution, it contracts. When it forms, it starts contracting. Once temperature is high enough for any fusion to start, so the first fusion reactions that happen in a star are deuterium fusion. Deuterium and lithium are the ones that capture protons easier, and then you have hydrogen fusion. You have a stable stage, and our sun is currently fusing protons or hydrogen in its core into helium, and we are able to date the sun, which is about 4.6 gigayears old, and so we know that there are about 6 gigayears left or a bit less until the sun exhausts the hydrogen in its core. Once it exhausts, it contracts again, and until again it's able to reignite nuclear reactions. Okay, so it's just like a pulsing. You could see it as a pulsing, or it's a lost battle against gravity, more or less. In particular for massive stars, and nuclear reactions will never be able to win gravity forever. You will need to go in the dead stars for intraatomic forces in order to hold gravity. So the interplay between the contractional energy and the nuclear energy generation appears in the course of stellar evolution, and as the nuclear energy generation rate is very sensitive to the temperature, as I told you, you don't fuse carbon at the same temperature as hydrogen, and you need much more energy to fuse carbon. Then you will have a follow-up, a sequence of nuclear fusion stages that will go on as the star evolves. Okay? So I will mix a bit the nuclear reactions and the history and stellar evolution, and I hope I don't lose it in the way. I tried to do it something. Well, let's see if my mind labyrinth is compatible with yours. So 1938, these guys, Gamow again and Better again, but here is von Weizsäcker, they identified the fusion path for hydrogen, and there are two fusion paths for hydrogen, what we call PP chains and cyano cycle. Let's look at it. In low mass stars, like the sun, so normally the product of hydrogen burning, okay, I said burning, so just now you know, of hydrogen fusion burning, aka burning, is helium. So the net product is that you use four protons, and you build one alpha particle. But you cannot do it right away. You have to go through a series of reactions. And the first series of reactions, which happens at quite low temperatures, meaning temperatures of about 10 million degrees, 15 million degrees, is what's happening in the sun, in the sun, and also in the first stars, because in the first stars, you just have hydrogen and helium, so you don't have another way to fuse hydrogen. And here are the reactions. So you have the elements. So the blue ones are protons, the green ones are neutrons. You have positrons, neutrinos here, the small balls, electrons in red. And what you have also, which is quite interesting, is the percentage of the different probability to go through one path or another. So pp1 chain, 86% of hydrogen 3, 14% of the hydrogen 3, which is the yield of the first reaction, goes into the pp2 branch and pp3 branch. All of these branches yield the production of an alpha nuclei, sometimes two alpha nuclei. Okay? The important thing here that you can look at is the times here. So when you have a nuclear reaction rate, you can always, which is a velocity with time, a number of reactions according to time, you can invert it and have an idea of the characteristic time scale you need for the fusion to happen. Okay? And what we see is that for the fusion of two protons to happen, and in the faster way, you need 10 billion years. So 10 billion years is a lot. And it's about the lifetime. It sets the path of evolution of low mass stars, meaning that the stars that fuse their hydrogen through this path, they will have a life, a duration. The phase where they burn, where they fuse hydrogen in their core, is of about 10 gigayears. It means that for the lower mass stars, where the temperature is not that high, they are as old as the universe. Okay? And so that's why when we look at very small stars with few metals, we have a good idea of a composition of an early universe. So there's a bottleneck here with the first reaction, and so the low mass stars live long. The sun will have a total hydrogen burning phase, which will last for about 10 gigayears. For M dwarfs, it can last for 15 gigayears, 20 gigayears. Actually, when you do stellar evolution computation, it can overshoot the age of the universe by far. Okay, so the stars that we observe now, they are just doing things very, very slowly. There's another way to fuse hydrogen into helium, and this happens in the core of more massive stars, and it requires that you already have carbon, nitrogen, and oxygen available. So it's not possible in the first stars. Okay, so the first stars, the very massive one, they did the pp chain. So this is what we call a bicycle, and we call it a cycle because at full cycling, meaning at high enough temperatures, you start here on carbon 12, you capture a proton, gives you a nitrogen 13, which is unstable, yields to carbon 13, again captures a proton, yields to nitrogen 14, captures a proton, yields to oxygen 15, which is unstable, goes to nitrogen 15, and again captures a proton and can go either to oxygen or to carbon, depending on the particle that you assemble it with. Okay? Either you just grab a proton and you emit a photon, and then you go up on your valley, you change line up. Otherwise, you emit an alpha particle, and so you go down in your stability valley. Okay?
So this bicycle cycles, and that's why carbon, nitrogen, and oxygen act mainly as catalysts. If you look, you have used 1 proton, 2 proton, 3 proton, 4 protons, and you end up with 1 alpha particle, so 1 helium. Okay? In this, there's also a bottleneck, and the bottleneck is this reaction, the nitrogen-14p gamma reaction. So capture of proton on nitrogen. It's very sensitive to temperature, and so this cycle will essentially yield to carbon-13, nitrogen-14, nitrogen-15, and a bit of oxygen-17. This is what comes out from these nuclear reactions. In this view graph, you have the reaction rates in colors, color-coded for the arrows. And what you have here, these boxes, they trace the neutrinos that are emitted by this beta decay. You remember this beta decay is when the weak force intervenes and you turn a neutron into a proton. Okay, you have this change, and when you do this, you emit a neutrino. Neutrinos are the ideal spies of the interior of the Sun because they interact very, very few with the matter. And if we are able to detect neutrinos, we can exactly know the conditions or temperature that are happening in the center of the Sun. And so that's the way we know the temperature of the core of the Sun, is by neutrino observations. And actually, in the Sun, this is a paper of 2020 by the Borexino collaboration, published in Nature. They actually identified the neutrinos coming from these reactions, and they were able to measure them, the energy and the fluxes, and so they were able to say to what amount the CNO cycle contributes to hydrogen fusion inside the Sun. Because I told you that inside the Sun is mainly pp chains, but as you know, as you understood now, I hope, nuclear reactions is a matter of probability. So there's always a non-null probability, but if it's very low, it won't happen. But in the Sun is here, the core temperature is of about 15 million degrees. You see that most of the energy is provided by the pp chains, but part of the energy is also provided by the CNO cycle because the Sun is metal rich. There are some carbon, nitrogen, and oxygen in the Sun. And so part of the hydrogen fusion occurs at a slower rate with CNO. What you see in this curve is that CNO depends, the energy production rate depends very strongly on temperature, meaning that the massive stars, or the stars that produce energy with the CNO cycle, evolve much rapidly, because if you have hot energy, if you have a hot medium, you have a high probability of having CNO cycle, so you fuse hydrogen at a very fast pace, much faster than pp chains. And so you may have stars, for instance, that are 20 times more massive than the Sun, that will evolve in a few million years. So you see it's 4 orders of magnitude less, faster than the Sun. So this is for hydrogen burning in the stars. Let's move on, because the problem is that we want to build the metals, so the heavier elements. Lots of work was done by Fred Hoyle concerning this, and there's a first seminal paper in 1946 that competed a bit with the paper, the alpha, beta, gamma paper, who said that we can do anything from hydrogen and, we have the primordial nucleosynthesis, and Hoyle said that all the other elements should also be formed continuing this chain. And in particular, it's a very interesting paper, because we don't write papers this way anymore. But he says here a scientific method for him to advance that there should be nuclear reactions that allow to build the heavier elements from the hydrogen. And he said that the procedure to be followed is the following. The chief aims of the present paper may be summarized. Find the value of density and temperature such that equations of statistical equilibrium give the required abundances of the elements over the whole range of the periodic table, show that a cooling expansion process can be found such that the value of density and temperature satisfying the first hypothesis can be reduced to low density and temperature, and find a place in the universe where the actual values of density and temperature satisfying this must occur. And so when you try to do this and do nuclear physics, you find out that you need a certain temperature, a certain density to build heavy, to overcome the Coulomb barrier of the tunneling. And so it's this seminal paper that gave the idea, and to him a bit for some years later, that you can go past hydrogen fusion. Another important thing is that in 1952, and I will come back to these stars, which are called AGB stars, Merrill discovered technetium. It was a very important thing, so that's the paper. Because technetium, if we go back to our nuclide chart here, it's this line, and as you see in this line, there's no black square, so no stable isotope. Technetium is not stable. And some of the technetium isotopes are long-lived, a bit long, but not that long. And so actually observing technetium in the atmosphere of stars means that there's nucleosynthesis going on, because this, from the early universe, it couldn't have survived. So if you see it, it's that it's been synthesized inside the star. So wow, there's a very rich nucleosynthesis, so rich that you can even build atoms that are as heavy as technetium. Okay? So the problem is that at that time, we don't know how to build them, because we don't know how to pass helium and mass barrier. But then comes Hoyle again, and he's quite famous for this, and we even talk about the oil transition, and that here comes what I told you, and maybe was a bit out of ground earlier this morning, about the resonances. I talked to you about it because there is a resonance in these nuclear reactions of the alpha particle that we exist, that the elements that here in exobiology, astrobiology, we are interested in, they are made because of this reaction, resonance. So Fred Hoyle identified that you can put up together 3 alpha particles to build carbon, and thus go beyond the unstable isobar of mass 8. And he predicted that there should be an existence of a transition in the carbon atom with a resonance at 7.7 mega electron volt. And so it goes this way. You have hydrogen 4 that captures another hydrogen, builds beryllium 8, but this is unstable, and so this reaction will go backwards all the time. But at some point, there will be, with a very low probability, the possibility that the beryllium 8 captures an alpha particle and enters the target nucleus of the target nucleus will be resonant, and so you will amplify the effect of this very scarcely, not scarce, but improbable. Even though this reaction is very improbable, once you have it, there's a resonance, so you magnify the probability of interaction by several orders of magnitude, and then you can build carbon-12. So we talked about hydrogen fusion. At some point, I told you that there won't be hydrogen left in the core of the star anymore. The core of the star collapses. Temperature increases because we have a perfect gas and volume is not affected, so you increase temperature. And so when you increase temperature, at some point you will be able, if you reach temperatures of 100 million degrees, you will be able to start helium fusion. So you are in a medium where you are in the ashes of hydrogen fusion. So no hydrogens anymore, no protons anymore left, only helium and some of metals. The main reaction that you can have is two alpha particles going together and building beryllium-8. But the thing is that, as you see, the Q value of the reaction, the energy produced by the reaction is not produced, it's consumed. It's an endothermic reaction. So you use the energy. So it doesn't stay there, and it's a reversible reaction. So you start doing this, but in the end, you never manage to go beyond the beryllium-8. So you have an equilibrium concentration that appears, but if the temperature goes beyond the 100 million kelvins, the proportion between beryllium-8 and helium-4 comes to 10 to the minus 9. So you have very few beryllium, but it's enough, the beryllium that survive are enough for them to capture the alpha particle with a resonance. And so this makes this jump very efficient, okay? And so this is possible thanks to the Hoyle resonance. And this is the notation I talked about before in the air. So this carbon-12 star, which is the compound nucleus in an excited way that will gamma decay to a normal carbon-12. So this is how carbon is formed in the universe. And once you have 4 carbon, you can go up to all the massive ones. The energy production rate of the 3 alpha is very strong because it depends on the temperature at the power of 40. So it's very dependent on energetic. And so each time you have a nuclear reaction that depends, the dependence of energy that are on temperature that I showed you, of the energy production on temperature, when you increase the exponent, it means that you accelerate the phase, the fusion phase, because you have high temperature, it depends very much on temperature, so you will fuse the helium very fast, okay? So helium fusion is much faster than hydrogen fusion. And the fusion of subsequent heavier elements is always much faster. So as you will see, when people talk about life of stars, they refer to hydrogen burning stars because in the end, the other phases, which are fundamental for nucleosynthesis, they are very short-lived because of this dependency of nuclear reaction rates to temperature. So the thermonuclear helium fusion is also accompanied by captures of alpha particles on carbon that yields both oxygen and neon-20. And this reaction rate, so here you have observations of reaction rates. This is the energy in the center of mass of the reaction. And this is the S factor, which is a part of the cross-section. And what you have is a model in red. And the points are measurements in experiments. And you see that you have several resonances making it, and some of them were discovered late. For instance, these 2 resonances were not known before 2005. So before 2005, we thought that at this energy, there wasn't any resonance. But then they were found experimentally. And so this changes a lot the yield of this thermonuclear reaction. And so the point is that it's unclear that what is the main product of carbon fusion. It can be carbon, oxygen, or neon of helium fusion. It's either carbon or oxygen, depending on the ability of the carbon that is built by the triple alpha reaction to, again, capture an alpha particle and build oxygen. You also build neon, and this neon will further alpha decay, emitting neutrons, and these neutrons will be important for another type of nucleosynthesis that we will go through. So first, red flag. From the nuclear point of view, we don't know yet very well the reaction rates, meaning that at some point, the evolution of stars can change completely if we discover a resonance or we change completely the nuclear reaction rates. And this will have effects all the chain into the production of carbon, nitrogen, oxygen, phosphorus, and whatever for life forms. Okay, so it's very dependent. Now we know how to pass through this helium burning barrier, how to go to carbon, and we can go further. And here comes a great lady, which is Margaret Burbidge, here in the center with his Fred. He's her husband. So this is, I don't know his name actually, Burbidge, Mr. Burbidge. For once, it's the lady first, so it's quite an achievement in '57. And this is Fowler, William Fowler. And so this paper has been cited, I don't know how many thousand times. If you go to the ADS, you will see it. And it explains the general shape of the cosmic abundance that we saw. They propose all the successive reaction and also the neutron capture reactions to explain not the heavier, but the heavier elements. So let's go to these nuclear reactions a bit quickly. You will have, once you don't have helium anymore, again the core contracts. If the star is initially as the sun, the core contracts, but the mass is never high enough for the core to reach temperatures that will allow carbon to fuse. And so it will stop there. It would stop there. It's a dead star. You do not produce thermonuclear energy anymore, and you sustain the star by the pressure of the electrons that are just stuck in their quantum cells. Okay? This is a white dwarf. This is what the sun will become. But for more massive stars than the sun, typically stars that are 10 times more massive than the sun, the temperature, once the helium is exhausted in the center, will get high enough for carbon fusion to be made. And beyond carbon fusion, you will have neon fusion and oxygen fusion, or burning. And so each time you are left with the ashes of the previous nuclear fusion phase, it means that you do not have light particles anymore. So for carbon burning, you do not have neither alpha particles, neither protons. So you have to combine the carbon-12 abundances. It yields to magnesium-24 in an excited state. And so the main ashes of carbon burning will be neon and sodium in equal ways, because there are also uncertainties that we do not know much. After carbon, it's not oxygen that will fuse, because oxygen is a double magic number nuclei, meaning that you have closed shells of neutrons and protons inside the nucleus, which makes it very stable. So it's difficult to fuse. You need more energy. So you first fuse neon from the carbon ashes, and you will mainly produce oxygen and magnesium. And after that, you will have oxygen burning from the ashes of neon burning, and this will produce phosphorus. The phosphorus we are looking for is essentially produced in oxygen burning, which occurs then only in massive stars. Okay, a star like the sun. If all the stars were to be like M dwarfs and like the sun, we would not have phosphorus to build any of the living things. So we need the massive stars to do this. And afterwards, we will see that once the silicon wants to fuse, there's no fusion anymore, because silicon yields to iron, and iron then cannot fuse anymore. So here I go very quickly. These are the major burning things. It's just to show you that for neon burning, you will build oxygen, you will be silicon. For carbon burning, you will essentially synthesize neon and sodium. And for oxygen fusion, you will synthesize the phosphorus. So now you know where the CH and OP and S also, because here you do the sulfur, where they come from. So they come from these nuclear reactions, and these nuclear reactions happen in massive stars. Okay? So these very important elements. Most of them come from massive stars for the carbon, oxygen, phosphorus, and sulfur. The nitrogen comes also from low mass stars and, because of the CNO cycle. You remember, you do nitrogen 14. If we look at a star that will go through all these phases of thermonuclear reactions in its core, this is a model for a 25 solar mass star, you will have what is referred and that you can visualize more or less here. You will go through hydrogen burning. Then when hydrogen is exhausted in the center, helium burning comes in, but there's still lots of hydrogen around the center, okay? And around the center, as the center has been contracting, the temperature also raised just in a shell around the core. And so you have a core which is providing energy with helium burning, but it's surrounded by a hydrogen burning shell, okay? Because there are lots of hydrogen. The hydrogen is exhausted in the core, but all the rest of the star is full of hydrogen, as in the beginning. When the star contracts, the core contracts, but the temperature does not make a step profile. You know, it's a continuous profile. And so you have very strong temperature in the core, but then in the edge of this core, the temperature raised sufficiently again for having hydrogen burning, not in the core, but in the periphery of the core. And so this way, for these massive stars, you build what we call an onion shell structure when they finish their evolution with an iron core surrounded by shells of fusion of silicon, oxygen, neon, carbon, hydrogen, helium, and a great envelope of nothing happening in terms of nuclear. And why I show you this is for you to have a grasp on of the physical conditions that are reached in these stars and the timescales involved due to, the dependence of the nuclear cross-section reactions to temperature. You go from temperatures to 60 million degrees to 4 billion degrees, and with time of each of these stages that go from here 7 million years for this star to 1 day for silicon burning, and then a few minutes for what happens after, and that will be the explosive nucleosynthesis. What happens then? So we have seen that in these massive stars we can go up to iron, but then we are lacking all the other elements, the very neutron-rich and heavy elements. And these are made by neutron captures. So these neutron captures, they can occur in two ways. Either the neutron capture is slow, meaning that the neutron capture characteristic timescale exceeds the timescale of beta disintegration. You capture a neutron and you keep it inside before you decay, okay? And so you build a stable element, which is what we call the S process. So you move like this in the nuclide chart, okay? This S process, S process. So this S process occurs when you have a density of neutrons of about 10 to the 8 neutrons per centimeter cubic, with a time scale which is of between 10 and 1,000 years. And it happens inside the massive stars, but also inside low mass stars when they are very evolved. And I will show you in the next slide why it arrives. Not in the next, but in following slides. There's another way to build the most massive, like gold, for instance, neutron-rich elements, which is the rapid neutron capture, the R process, and it's responsible for the other half of heavy nuclei in the universe, and it requires very high temperatures and densities, and it's very short-lived because it happens when you decay immediately. So you capture a neutron, you decay. You capture a neutron, you decay, and that's how you climb up in mass. Okay, this is the R process. For a long time, we thought that this R process was mainly made by exploding stars. I will show you in a minute when these stars explode. But it was theoretical, and we didn't really observe that much R process nucleosynthesis in the light curve of supernovae. And so it was a puzzle until 2017, very recently, where we actually observed the merger of two neutron stars. There was a gravitational wave event, and there was a trigger to all other telescopes to point in the direction of the gravitational wave event. And the actual optical counterpart of the event was observed, and light curves were determined. And there we saw lots of R elements. So now we think that these R process elements, they are formed in the merging of compact stars, compact dead stars, neutron stars merging, or black hole merging, or black hole and neutron star. These processes, they go for all these stars, all these elements. So you have the R process, a first peak, a second peak, the lanthanides, a third peak. And all these are built in these very energetic events, either supernova explosion or fusion of compact objects. So to make a wrap-up of the nucleosynthesis sites, we now know that when we go back to the cosmic abundances, we have the very light elements that come from Big Bang nucleosynthesis. Thermonuclear fusion explains all the elements up to the iron peak elements, which are here and stable because of nuclear statistical equilibrium, because of their binding energy, which is so strong. And then everything else is made with neutron or proton, but essentially neutron enrichment processes, which is the R processes, rapid capture, or slow processes. Okay? So now we know where we do everything. So you might ask yourself, so for these elements, I told you that it's when the stars explode or when you have fusions. So you might think, and that's actually happening, is that when you have such extreme events, you throw into the interstellar medium all the matter of the star. And so it's easy to see how you expel these elements that have been built inside the star in the interstellar medium, where they will be available for slow, low temperature chemistry to assemble as molecules, as grains, and serve into the production of new stars with their planets and everything. Okay, so this is the cosmic recycling, and we know well for these very strong events. But for all these stars, I told you that the fusion occurs in the core of the star. Yet we see these elements in the universe. Okay? We see nitrogen, we see carbon. And so at some point it means that it went from the core of the star to the surface of the star and was lost into the interstellar medium. And this is stellar evolution, actually, that allows us to build what we call the yields, which are the amount of elements that are produced and expelled back in the interstellar medium by different generations of stars. So now that I showed you the structure and the nuclear reactions inside the stars, I will talk about evolution for you to know when or where in the star these nuclear reactions happen and how the products of this nucleosynthesis goes back into the interstellar medium. So we are really lucky, and that's a great thing, is that when we look at the sky, beautiful sky, and look at with instruments and build what is called the Hertzsprung-Russell diagram, which was thought of in the early 20th century. Stars are not put on. This diagram is a diagram where you have temperature in abscissa and luminosity, so energy radiated in ordinate. In the abscissa, it's reversed, meaning that the hotter stars are here on the left and the cooler stars are on the right. Okay? when the first time Hertzsprung and Russell did this, they saw that they weren't expecting anything, but if you don't know and you look randomly at stars, you would expect a random distribution, so points everywhere. But there are not points everywhere. And they found that there's what they call a main sequence. So the main sequence is actually, now we know, it's identified as the region of stars that are fusing hydrogen in their core, as hydrogen fusion is the longest, has the longest time scale for the fusion to occur. This is where the stars spend most of the time. So that's why we see that many, because they are most of the time spend the essential of their lifetime in this region. Here down you have the M dwarfs, and up here you have the O-type stars, so the very hot ones. Then there's this giant branch, which is where the low mass stars like the Sun evolve when they out of hydrogen in the core. And it's a branch, and it's red, and the stars are very, because of the link between luminosity, radius, and temperature, the stars that are red and very luminous, they are very big, and so that's why it's giant, okay? So red giant branch. And here down, it's very hot, nearly white, and it's very compact, and so it's a dwarf, and it's white. Okay, so it's not very complicated in stellar physics. The names are really... So you have giant, supergiant, hypergiant. No, I don't know if we find an even bigger one, how we will call it, but something bigger than hypergiant. And we have the red dwarfs, which are the M stars, the white dwarfs, and the brown dwarfs also. So it's very colorful. So why I show you here, it's because when you see it and when you go back to the literature of the early 20th century, people did not interpret this as an evolutionary path, or they interpret it as an evolutionary path which is very far from what we understand now. But actually, this is an evolutionary. This allows us to trace the evolution of stars, because what you see here is a bit what you see here. Here is a random picture of, I don't know, of cousinade, as we call in French, which is when you gather the large family with all the cousins of up to fourth degree of cousins, and so you have children. You might have babies somewhere, you have elders, you have people of just median age, you have everyone at once. And so when we look at the sky, it's the same but with stars. We see baby stars, we see very old stars, we see stars in their middle ages. And so looking at everything and putting it together with the equations of stellar structure and nucleosynthesis and nuclear physics, we are able to say that a star like a Sun will evolve from one place to another to this diagram. And the fuel of the evolution, as I told you, is thermonuclear reactions. So the contrast is not very good, but I think it's enough for you to see that the nucleosynthesis we saw, it depends on stellar mass, and the nuclear reaction fuels the evolution. The Sun would be this line. So you have a protostar. All these are the protostars, so stars embedded within a shell of gas and dust. Then the star becomes a real star, a pre-main sequence star like the Sun. Then it comes out of hydrogen in the core. It becomes a red giant, so the core contracts but the envelope expands. It's called the mirror effect, so it becomes big. It fuses helium, and at some point it runs out of helium, but it's not massive enough to go beyond and have fusion of helium, and so it makes a white dwarf that expels, there's lots of winds, expelling the envelope of the star. So you form a beautiful planetary nebula, and you are left with a white dwarf. If you have a more massive star, their evolution is not that well understood, but in the end they will explode. And you will be left up with neutron or black hole. So you see that all these final stages, they involved at some point that you give back to the interstellar medium part of the matter that was imprisoned in the star during several million or billion of years, but the matter you give back has been nuclearly processed, and so it's been enriched in metals. So this is how you form the metals in the cosmic evolution. So the low mass stars, they never reach the core densities to go beyond helium fusion, and the massive stars, they go up to the entire series that we saw. Here you have a more physical diagram that shows it. You have the density in logarithm inside in the core of the stars, the temperature in the core of the stars, and here you have the evolutionary path of stars of 1, 2, 7, and 15 solar masses. And what you see, this is the curve of hydrogen ignition, the famous Gamow window that I showed you out of the blue earlier. Now you know where it comes from. So this is the region where the Gamow window is best, so where you can have fusion of hydrogen, Gamow window for helium, Gamow window for carbon ignition. And you see that the massive stars, they go all the way through this, while the less massive stars, they are stopped here. They are stuck here and they do white dwarfs. So in a nutshell, for the sun, what happens? The sun forms out of a cloud. It goes by, it contracts, gets rid of his shell, builds up planets, all the things you are interested in, arrives here, burns hydrogen, gets out of hydrogen, moves to the giant branch. You have an inert core of helium. Temperature raises in the center. Helium starts fusing in the center. You are here, at the clump. Then you get out of helium. You start again climbing, and here the energy is provided by your hydrogen burning shell and helium burning shell, because as I told you, the temperature is not high enough to fuse helium in the to fuse carbon in the core, but it's high enough in the periphery of the core to go on fusing helium and even further from the core, hydrogen. Then here the star is very luminous and very expanded. Its radius is very large, and so the outer regions of the star are not gravitationally bound anymore with the star. There's lots of mass loss, which is quite uncertain, the amount of mass loss. And this mass lost will come and pollute the interstellar medium and bring the new elements that have been produced inside. But this envelope, you will say, it's really far from the core. So how does it work? It works that each time the star begins, each time you go at the end of a core fusion, the core contracts, as I told you, but the envelope expands. And as the envelope expands, it becomes red. It becomes red, and it creates a very big gradient of temperature. It's very cool at the surface, very hot at the center. Here again comes your boiling water pot. Okay? It's very hot down, very cool up. You have macroscopic movements, convection that appear, and this convection will drag, it's what we call the dredge-up events. It will drag down the regions where nucleosynthesis appear, and will mix all the envelopes, so that in the end, when you lose this envelope, it will actually bear the products of the nucleosynthesis that happened in the core of the star. So there's a way for the star to mix parts of its envelope so that it enriches the interstellar medium, okay? And so our knowledge of the enrichment of the interstellar medium is closely related to fundamental hydrodynamics, because if we do not understand how convection works, how turbulence mixing work, we are completely off in terms of the amount of carbon, for instance, or nitrogen you will put into the interstellar medium. A massive star evolves a different way, as I told you. It just builds an onion. So you have main sequence, then you have the core helium burning, you build the onion shell, and in the end, you explode. And this is what you put into the interstellar medium. So you put helium, carbon, nitrogen, oxygen, fluorine, neon, sodium, phosphorus, sulfur, and lots of interesting things back in the explosion. I will come back to the explosion in a few slides. This is lonely stars. one of you, I don't remember who, is working on multiple stellar evolution, or multiple, how it works when stars are multiple. Lots of stars live in binary or more than two in systems, multiple systems. And so during their evolution, they will interact, and there will be more phases for the envelopes to be stripped, and so to enrich the interstellar medium. And so it's very important to account for binary evolution when you want to understand the global evolution of the galaxy. These are two pathways for binary evolutions. This is massive stars evolution. If you have two massive main sequence stars, but with different masses, there's one that will evolve a bit faster than the other one. It will become a giant at some point, and due to interactions here, tidal interactions, you will put part of its envelope will be stripped and will go to the other star. So you'll strip the star. This star at some point it can explode, make a neutron star that you will observe in X-rays. And in the meantime, the other one, which has become bigger because of accreting material, will also become so big that it will engulf the neutron star. This is what we call the common envelope. So you have a neutron star inside a normal star. So this leads to the expelment. How do you say? Or you get rid of the envelope, whatever. Then you have a neutron star, and again, you have the same thing as you did here, but with compact objects. And you have a recycling neutron star, and they will fuse eventually, and this is a gravitational wave event that you will observe. Okay? So when you observe this, which is the last thing we observe, all this has happened, lots of nucleosynthesis has happened, and so you can know what happened in the massive stars. This is the common envelope evolution of low mass binaries, where you always have these moments where stars interact, and they will yield another type of supernova, which is the type 1a supernova here and here. So they exchange masses as they evolve. So just to put everything back in context, hydrogen fusion, it occurs in the core of the main sequence stars, by cyano cycle for massive stars, pp chains for low mass stars. And it also occurs in the hydrogen burning shells, and it's the nucleosynthesis of the hydrogen burning shells that gets expelled in the interstellar medium. The one in the core stays in the core. It's just like Vegas, you know, the core of the star. So it stays here, and it never gets disrupted unless it's a massive star that fully explodes. So this specific hydrogen burning occurs in main sequence stars and in the periphery of cores in several more massive objects, more evolved. The S-process nucleosynthesis that I told you about before, so the slow capture of neutron to make heavy elements, happens in these asymptotic giant branch stars, which is the Sun will become one, where you have a carbon core which is not hot enough to have fusion, surrounded by an helium burning shell, surrounded by an intershell, surrounded by a hydrogen burning shell. The thing is that here you have a diagram with time and mass coordinate. You have the core of carbon and oxygen, and here you have the hydrogen burning shell and the helium burning shell. And the thing is that the pace of this, because of the rates are very different, they don't evolve at the same pace, and from time to time, the helium burning becomes unstable. There's degeneracy, and so there are what we call thermal pulses, a flash here. So there's a convective region that develops and engulfs part of the products of hydrogen burning into helium burning. This yields to the production of carbon-13 and nitrogen-22, neon-22, that produce neutrons. And these are the slow neutrons that you want to build up the S-process elements. So they are built up here, very deep inside the star. So how do they end up early? Dredge up. This convective envelope, it's like a piston. You inject energy, you lift the envelope, and then when the energy quenches, the envelope goes back down. And if it goes back down a bit deeper than it was before, it brings up, it dredges up the nucleosynthesis. And that's shown here, but you don't see, so I pass. So let's put this in the context. I will have to speed, but I think it will be okay. Let's put it in the context of the general evolution of the universe in the end. So we've seen that the products of stellar synthesis end up back to a certain point in the interstellar medium when they are expelled by stellar winds or at the end of the star. So in AGB stars, I told you about the thing. So this is an AGB star. It's Mira Ceti, a specific star. It was observed with GALEX, which is a UV observatory that was meant to study galaxies, nothing. But they pointed to this star and they saw this kind of cometary tail. So it's not a comet, but the star is moving rapidly in the galaxy. And here you see all the material that is it's kind of a coma that is being expelled in the interstellar medium. Here, the resolution is not good, but it's another very known AGB star for which we have measurements of all isotopes for almost all elements. And you have the star, and it's enshrouded in a dust snail-like structure, spiral structure. In AGBs, which is important for us and for astrobiology, is that these stars, they produce carbon. They are a huge factory for carbon-12. And this carbon is built in an environment which is cool enough for molecules to form and grains to form also. So these AGB stars are very important because you have a continuum between nuclear physics here, then matter being brought by the dredge up to the surface, and this matter being lost to the interstellar medium, where you have enough seeds to build complex molecules. For the massive stars, everything happens in another kind of Big Bang. After silicon fusion, you form iron nuclei, but they cannot fuse anymore, and you have photodisintegration of these particles, which is endothermic. So most of the energy lost in the supernova is not photons, it's neutrinos. You emit lots of neutrinos, and you have a collapse of the core. So you lose lots of energy. So the gravity is winning because instead of, when you fuse hydrogen, instead of putting back energy, you consume energy. So you help gravity. So everything is going down in the core, but the envelope is not going down that fast. And so you have several speeds, and the envelope goes down at a high speed into the proto-neutron star in the center, and it bounces back. And this is this bounce back that yields to the explosion of the star, which is the supernovae. You have a runaway. All the matter becomes a neutron matter. That's a neutronization, emission of lots of neutrinos, and the total energy is equivalent to the energy to the luminosity of a galaxy, an entire galaxy. When we see a supernova explosion, it's super bright, just one star. And so this way you will expel in the interstellar medium not only everything you built in your shells, in your onion shell, because your onion shell will be blown up, but it will also be crossed by very energetic fast particles, and you will have our process, but also other processes, P process, alpha process, so other processes of enrichment and production of these very high, very heavy elements. So this is what is produced. Here you have a simulation just after of what we call explosive nucleosynthesis. Sorry for the microphone. And what you see, it's inside a star, and what you produce. So you produce essentially nickel, lots of nickel, titanium, and this is how we characterize, we verify the explosive nucleosynthesis, because this is seen in the spectra of electromagnetic counterparts of supernova explosions. So these massive stars will
put back in the medium helium, carbon, nitrogen, oxygen, and S-process nuclei. They were also, all the iron peak elements come from here, cobalt in particular, nickel, fluorine, air-process nuclei, and the even more massive elements, silicon, sulfur comes from there. Okay, and you have also a process, a neutrino-induced nucleosynthesis, which yields to boron and fluorine when these stars explode. There's another explosion, which are the type 1a supernova I told before. It's when you have a binary evolution of a low mass, and you have accretion on a white dwarf, and at some point the accretion becomes unstable and the white dwarf explodes. This is supernovae type 1a. They are very famous because they are called standard candles, and they are used to measure the Hubble constant, so the size of the universe. And so when you have this explosion, you will in particular contribute a lot to oxygen and to heavy elements like cobalt 55. Here it's a numerical simulation of this explosion, and you see the yield of cobalt, how it appears in the ejecta when the star explodes. For the R process element, I showed you that it's now probably understood as produced by the fusion of neutron stars. How do we know it? So for this gravitational wave event in 2017, all the optical telescopes were pointed to the region, and the optical counterpart was observed. It was a kilonova, what we call a kilonova. And what was observed were these spectra. And in particular, cesium and which one is TE?
Cesium.
Sorry?
Cesium.
Cesium and TE? Tellurium. Okay. So these are air process elements, and they are observed in these light curves. You see the lines here. The spectroscopic lines are clearly identified. So there's a production of these elements. The mass ejecta was quantified, and so now we think, since 2017, we have an observational probe that air process occurs in these captures, in these events. And here is what we saw, okay? So there was a gravity wave. Before the gravity wave, they put the telescopes in the region. Nothing was there. 16 hours after the gravity wave signal was received to Earth, you see here a small pixel, bright pixel. This is a kilonova. So this is a galaxy. So you see the amount of light that you emit in such a tiny event, because neutron stars are very tiny stars, but lots of energy. So now you see all this, and I'm as it's late already. I think that it's better that I do not go. I have a few more slides on galactic chemical evolution, but I will skip them because I think otherwise it's too much, and it will be too long. But now I think you have an idea of how it works from the nuclear physics inside the star on where these elements are expelled. The thing you have to keep in mind is that there are lots of uncertainties from nuclear reaction rates, from mixing processes, convection, how deep it goes, how efficient it is, and for mass loss. We don't know very well the mass loss of stars. So everything that we try to reconstruct on the chemical evolution of the galaxy and how the elements end up in certain regions where they will be used to build up new stellar systems and exoplanetary systems is quite uncertain and may change a lot according to the developments of the stellar physics, hydrodynamics, and nuclear physics. So that's why it's very exciting. It's a very exciting topic because you have lots of things intertwined. And then comes chemistry later on, which is what most of you are interested in, and that I don't know much, but now you know where the building blocks come from. And I thank you very much for your attention. I hope I didn't lose you too much, and thank you for the travel with me.